Hello everyone, today I'm gonna talk to you about our work on Neuro-Symbolic AI for analytical solutions of differential equations. Let me begin with why that matters. Let's consider a damped wave, a solution that arises in acoustics, vibration, and many dissipative systems. A closed-form solution does more than describe the field. It makes the dependence on every parameter explicit. The oscillation through the wave number and frequency, the amplitude decays in time. That interpretability is why closed-form solutions remain the reference standard. But if they are so valuable, why are they rare? Because the problem of discovery is combinatorial. A solution is a particular combination of elementary functions, operators, and structural algebra, and the space grows rapidly with complexity. Manual derivation doesn't scale, and the existing automated approaches, symbolic or neural, haven't resolved it. That combinatorial explosion is the bottleneck we address. Our idea is to replace discrete search over expression trees with a continuous search over a smooth manifold. We embed every admissible expression into the manifold and explore it via gradient-based optimization. In other words, we transform combinatorial tree search into geometric exploration of promising region rather than enumeration of symbolic trees. So, how is this manifold built? It begins with a context-free grammar. Applying its production rules yields expressions that are valued by construction. Here, a two-dimensional eigenmode, and translates into a sin pi x of sin pi times y. Crucially, we do not search over the raw symbols that the grammar produces. We search over atoms, complete physically meaningful building blocks like spatial eigenmodes, temporal factors, transition layers, and localized profiles. Searching over meaningful components rather than individual primitives is what makes the space tractable. To search these atoms efficiently, we embed them into a regularized latent manifold. Nearby points share a similar grammatical structure, so symbolic search becomes geometric exploration. Each atom is also tagged by its structure. That manifold is built a single time for all problems, using only symbolic expression and no simulation data. At inference then, the inputs are a differential equation, its conditions, and one high-level ansatz specifying the structure of the solution. The output is a closed-form expression that drives the PDE residual to 0. What the ansatz does is to restrict the search. It defines slots, each requiring atoms of a particular type, as well as the structural tags that are needed before any candidate is evaluated. Specifically, it let us keep only the admissible atoms for the specific problem we have to deal with. And now, with the space restricted, the search proceeds in two stages. The first stage begins with the solution structure. For each slot, we cluster the admissible atoms. Then, we decode the representative from each cluster. And finally, we assemble the components through the ansatz and square the candidate by the PDE residual. The most promising cluster is repartition, and the procedure repeats until the structure is determined. Once the structure is fixed, the second stage refines only the numbers. The structure becomes a parametric function, and its coefficients are optimized by gradient descent until the residual reaches 10 to the minus 8, so we can have an exact closed-form solution. But that is the method, and the rest is what it can do. So we begin with problems where the analytical solution is known and exists. Let's consider for that goal once again the damped wave. On the damped wave, SIGS recovers the exact closed form at a relative L2 error of order 10 to the minus 13, while the neural baselines and the symbolic baselines range from several percent to over 1000% error. Recovering a known analytical solution is reassuring. The harder question is whether the method helps where no analytical solution is known. So, we test the Poisson equation with localized Gaussian forcing. Comparing against the finite element reference, SIGS recovers a compact symbolic approximation at 1 to 3% relative error, with interpretable boundary compatible structure. Beyond accuracy, we asked also if the method is robust when the grammar itself is incomplete. For that reason, we consider the KDV soliton, which is naturally written with hyperbolic secant squared. We remove the hyperbolic secant and hyperbolic cosine productions from the grammar entirely, and we figure out that SIGS instead can recover 2 minus 2 hyperbolic tangent squared. which by a standard trigonometric identity yields the same function. Therefore, search finds an equivalent representation despite the missing primitive. Finally, to test the limits of this method and see how far does this scale, we tested the method's capabilities on fully coupled nonlinear systems. And for that reason, we considered the two-dimensional shallow water equations, where the density and both velocity components appear in every equation. SIGS managed to recover all three fields. Shown are the reference and the recovered density and velocities, with relative L2 errors below 0.05% each, in roughly 3 minutes. To our knowledge, this is the first symbolic method to address such systems. To summarize, SIGS turns analytical PDE solution discovery into search over a learned symbolic manifold. It recovers exact solution, produces symbolic approximations where no closed form is known, finds equivalent forms when primitives are missing, and extends to coupled nonlinear systems. Thank you for your attention.